Thank you very much for having me. I really appreciate it. So what I'm talking about today is generalization of a result that I proved in my PhD thesis. So the main result is the following. The result from my PhD thesis is the following. So there exists a functor from DP-Co of a one-parameter family of genus 2 curves. To a subcategory of the cohomological Fukaya category. So it's the Fukaya category of a symplectic fibration. So that's known as the Fukaya-Seidel category. And this is a one-parameter family of symplectic fibrations, where V naught is a holomorphic function, and I equip this with a symplectic form, a particular symplectic form, and then I look at a one-parameter family by scaling that symplectic form. So in my joint work with Azam, Heather Lee, and Melissa Liu, what we're doing is we upgrade this result and adapt it to apply all full 6 parameters of the moduli space of genus 2 curves, varying the complex structure. And correspondingly, this also means we're varying the symplectic structure on the mirror symplectic fibration. So the outline for today is 3 parts. I'll give some background on homological mirror symmetry by example. So I'll be doing the elliptic curve. And this example is important for understanding what follows, which is why I'm starting with it. So then I'll say a little bit about what goes into my thesis result, which is essentially upgrade T2 to T4, and then on the complex side, look at a hyperspace, a hypersurface, and on the symplectic side, look at a symplectic fibration with the mirror T4 as a fiber. And third, I'll talk about my work, my joint work with Azam, Lee, and Liu. Okay. So the idea is I'm going to use a result which was known by Zaslow and Polishuk from their paper Categorical Mirror Symmetry for the Elliptic Curve. So the mirror to a T2 is an elliptic curve. So we have on the left side here, we have what's called the A side. So this is the symplectic geometry. And on the other side, we have the complex mirror. So we're looking at the complex geometry on a mirror. So on the symplectic side, in dimension 2, this is determined by the area of the symplectic form. So we start out by looking at the area as a real number, so we haven't complexified the Kähler form. And then on the B side, the mirror is an elliptic curve, which we can assume one of the basis of the lattice is 1, and then the other one is something in the upper half plane. And for this to be a mirror, we want tau to be I times A in the upper half plane. So a remark on this, because the upper half plane has, if we allow it to vary, the modular parameter to vary, there's 2 real dimensions in which it can vary. And right now it looks like the area of the symplectic T2 only has 1 parameter. And so the second parameter corresponds to adding a B field. So the dimension, the real dimension of the moduli space of complex structures is 2. And so the analog on the A side is this B field. And instead of omega, we add an additional form B, and this allows us to then vary tau in the upper half plane. So the upshot is geometrically, the mirrors are T2 with area A. So for now, I'm going to be working without the B field. This is mirror to the elliptic curve with this lattice. Okay, so homological mirror symmetry is this algebraic statement, which says that the bounded derived category of coherent sheaves on the elliptic curve is isomorphic to a category called the Fukaya category on the symplectic side. So let me describe what this is. So the objects that we consider are closed Lagrangians, up to Hamiltonian isotopy. So Lagrangian is just a half-dimensional submanifold on which the symplectic form vanishes. So you could think of it as, say, if you have a complex manifold, it's like the real part. Locally, it's like the Rn versus I times Rn. So in this case, this is just going to be closed curves. Anything one-dimensional on a surface only has one tangent direction that we plug into the symplectic form. And the symplectic form is an alternating form. So omega is a non-degenerate closed form. And up to Hamiltonian isotopy, that means that we have a vector field which is dual under contraction to a smooth function. And if we consider the flow of this vector field, then we say that L and P T of L are equivalent objects in the Fukaya category. So because we're considering up to Hamiltonian isotopy, we can take our objects here to be, since they're closed, rational slope lines. And this looks like the following. So we'll call the one of slope 0 L0. The one of slope 1 we'll call L1. Then here's the one of slope 2. This is wrapping around the torus twice. And we also have a vertical Lagrangian. So if we call this direction C and this direction theta, we have this vertical Lagrangian at some sake C0. This is mirror to an object in dB co, namely the skyscraper sheaf O C0, such that log of C0 is C. So there's more than one Z0 with this particular Xi, and that corresponds to adding a local system as part of the data on the Lagrangian. So in other words, a flat unitary connection on the trivial line bundle on the Lagrangian, which here is just going to be a number. If you look at the holonomy of that flat connection, and so that gives us S1's worth of Lagrangians and local systems corresponding to the S1's worth of choices of Z0 with that absolute value. So the intuition for the Hom sets here. So we have the morphisms, we have the objects now. We want to describe the morphisms of the Fukaya category. So these morphisms should match with the morphisms of DB-Co, which are the X groups. In particular, this line bundle L is that on the elliptic curve of degree 1. And so the claim is that a slope 1 linear Lagrangian corresponds to, under homological mirror symmetry on objects, this line bundle of degree L. And in order for that correspondence, we need the X group to be isomorphic to the Hom in the Fukaya category between Li and Lj. So Li is going to match with L tensor I on the complex side. So the Hom groups in the Fukaya category are intersection points. This is called Plur homology. And it's a chain complex generated by these intersection points. So this is a chain complex, and this is actually the homology. And the reason these are equal is because I'll say more about the differential when I go to section 2 and 3, but the differential here is 0. So it counts bigons analogous to how we will count triangles in this example. So the differential is something where you input an intersection point and you output a sum over intersection points. So you have an intersection point and another intersection point, and you count the bigons between those two. What we're going to have in this example is we have composition of morphisms. And so that's going to input 2 intersection points and output a sum over intersection points. So this 2 here and the 1 point here, that tells us that we have triangles between 3 intersection points. So before I do that, I just wanted to say why this is natural, that these intersection points should match up with the X groups. And the reason is something known as family Floer theory. So of Fukaya and Mohammed Abu Said. And this is a way of building a mirror by defining your mirror so that the morphism groups are isomorphic. So if you recall in this picture, we have this vertical Lagrangian, and we have other Lagrangians like this. So any slope Lagrangian Li, integer slope, intersects this vertical Lagrangian in one point. Which is determined by the C where this is at. So the X skyscraper is in the case, sorry. So this intersection, you can put degree bundle. So this is Fukaya. Abelian cities. Of looked at the Fukaya L to of section for J of sections. We can map the intersection J minus a function. I have count. So we have a category. A L. So this is when of by to action point. And then theorem tells directly. Universal cut. This is here. And then we just count one. And ones that are we have is we find an action which brings us and what we find is functor, indeed a functor. This to 0. So side section and counting triangles coefficient. So P is the lattice point. These are lists of P, and this is B, and out. The same code. All right. Which is grade the new. GMS on T4 is not new. This is previously known, more advanced to doing bias paper. And in this case now, we have called T, edit as V. And this now, instead of where the R2 mod gamma B, R2 mod gamma B we're going to call TB. This is of the and of B vectors 2, 1, and linear slope Lagrangians are 1 exceeds instead of C2. And this now varies. Definition of this group, the on X1 gamma 1 times 1, 0, 1. And this T here is giving us the one parameter family. The line compatible with that it does fiber gamma B action on the base, and in the fiber following, and it multiplies lambda sends 1, 0 and 1, 2, and then it's of form. Find this inner product structure. That's what morphic structure is. Slope of line have tensor powers of this L and cap the so match up with L tensor I and vector spaces. Just multiplication. Or G minus I. Step 2 is to fit this into something about so that T4 the following. So we are small restrict is to just D is still differential is still 0. And 2 up to a 1 of 12. Can say that what we did above describes on category. Side. And here. And we Cannizzo. So this, and this is my country. Full symmetry that category defined. It is at this deep So what is who found a way to hypersurfaces of toric varieties and varieties. Has an points y1, y2, y3. Coordinates. And the way they were C2 a bit different. Half with is so we look at final action. Polytope. Half space. Here's the intersection. Toric varieties, but you have to quotient by this gamma. find. This is a generalized, called the generalized Zaslow to the genus 2 curve. And what it is polytope C2. Get this. If we call our three directions here P, product of get CP2 blown up at 3 points. Basically, work to curve SYZ curve. What that does is these around the U shape of LK, the Lagrangians that we consider play of this computation morphism gradation 2 curve from string finds the side homology. So this is how fiber is put this is an isomorphism for here. Now, and we pull what the theta chrome of what, which the that this map that tells us is fully map I ln. So in my this more generalized, we look at on B. And remember we had this hexagon tiling. The form P1 required to equal A3, the symplectic, which is now on the symplectic side, and behave when we shrink. And so this picture which then becomes this. I guess I'm out of time.
Don't worry, I think so.
Okay, I guess so. Now, just looking at parameters, a B field, so that B1 is real use a simplex and paragraph monodromy that's needed and this data in a nice way, and to keep track is this T are the and the so this is that if we L2Z matrix, that this so here where we take care of the wall crossing behavior that we're concerned with. So